let's consider what the gradient graph looks like. And we get this one a lot because this is a nice a tech active sort of question, because in this case we've given you what the actual function is, so you can put it in on your calculator. But in an exam we don't have to. We can just give you the picture of a graph and say, what's the gradient look like? So let's think about that. The gradient of this graph here is negative to that point there and 0 there. It's 0 at x equal to 2. So that 0 at x equal to 2, let's change the colour. At that point there at x equal to 2, that corresponds to that point there, all right? That blue section where the gradient is negative, well, that's here, all right? So don't forget that the vertical axis is f dashed of x, the horizontal is x. So down here, that means f dashed of x is less than 0. And here, that means f dashed of x is greater than 0. And right there, f dashed of x equals 0. Yeah? So this section here, I've got a positive gradient, okay, which corresponds to that section here, positive gradient, all right? Now, the other thing to remember is that was a parabolic graph, and it looks parabolic, so that means my derivative is going to be a linear graph. The power comes down by 1 each time. A cubic graph will have something that looks a bit more parabolic as a derivative, etc. All right? So what's this statement here? We see those key points there. All right? So the graph of f dashed of x or of dy dx against s, okay, so the area above the line has a positive gradient, the area below the line has a negative gradient, the intercepts correspond to a 0 gradient or a turning point, stationary point. All right, so they're just things to notice. Positive above, negative below, stationary on. Okay, if the derivative doesn't exist, we use an open circle. And derivatives won't exist for graphs that look like that, where they've got a sharp point or an apex, or where the graph is not defined. Maybe we decide to have this parabolic graph, but we do the domain between -3 and 2 not inclusive, and so it's not defined at that point there. All right. So, and this is really just saying the same thing. Okay, we go over it because it's important. There's the derivative is 0 at x equal to 1. At x equal to 1, the derivative is 0. Here, clearly the gradient is negative. Okay, sorry, what am I saying? Here, clearly the gradient is positive, all right, which corresponds to a positive value, which is above the axis. And here, my gradient is negative. It's a decreasing function, all right, and that corresponds to a gradient below the axis, all right. And that's just something to keep in mind. Okay, the gradient of a negative quadratic gives me a linear function. All right. What else have we got? Okay, consider that cubic. Sketch the graph of the derivative function. So what I'd like you to do is pause this and have a go at sketching this on your graph first, and then just see how you compare to the one that I'm about to do. Okay, well, welcome back. So let's just give me some colors. First points I'm going to draw in black this time is where the gradient is 0. Gradient is 0 there. Gradient is 0 there. Yeah. So that's where the gradient graph is 0. What have I got here? I've got a positive function there, positive gradient in that section, and I've got a positive gradient in that section. So those two parts correspond to that. Now, the steepness of those parabolic sections are not really relevant. It's just about is it above the axis or below the axis? And because this is a cubic graph, I expect my derivative to have a bit of a parabolic shape. We'll go green. This section in here, negative gradient. All right. So it's a negative gradient. So it goes down steeply to a certain point, and then it comes up. Okay. Now, for us, the location of this point here, okay, it corresponds to there what we call, it's also called a point of inflection actually, but it's not really a part of our course. All that really corresponds to, if you think about when we draw the cubic graph, I'm coming down, the line's getting steep until I get to a point where it stops getting steep and it starts to get flat again. All right. So that point where it gets as steep as it's going to be corresponds to there, and we never, unless you had to use technology to find out we'll talk about maximums and minimums later, you're not going to need to have to worry about that. All right. So hopefully, let's tidy up some of the bits and pieces that I had scribbled around. But hopefully your graph looks something a little bit like that one. All right, get into it.